What actually is a matrix in linear algebra, and do we really need matrices to understand linear transformations? Because most courses teach it backwards. You start with the matrix, and then after a while, you say that it represents a linear transformation. But the twist is that if you know what your linear transformation does to your basis vectors, then you know what the linear transformation does to any vector, and you don't need matrices at all. So then why do we actually use them? Well, because they're incredibly useful. And we're going to see in this video, I'm going to apply a linear transformation to a vector, and I will get, our normal result, but then I will try to simplify this method, and in that process, I'm going to construct a matrix. A matrix will just be made just in the process of us trying to simplify our method, and we're going to define vector matrix multiplication in such a way that's useful to us, and we're going to see that it's actually defined this way. So we're going to understand what the columns of a matrix actually represent, and we're going to also see what I mean when I say that the rows are expressed in a certain basis of W. So we're really going to construct a matrix from the ground up, and we're going to see that why they're not actually necessary, but why we use them and why they're actually super useful in linear algebra. So first of all, we really quickly got to talk about what a linear transformation actually is. And a linear transformation is just any transformation that takes a vector from a vector space V. So I'm just representing this vector space V, and we have a vector here, V from V. And then this linear transformation, T, takes this vector into a different vector, TV, from our vector space W. So for example, a linear transformation can take vectors from R squared and put them into vectors in R cubed. So it will take, it will take a 2D vector and change it into a 3D vector in a different space. But a linear transformation has to obey some rules. It obviously has to be linear, and how we usually write that is a linear transformation T on two vectors where V and W are vectors and alpha and beta are scalars. I'm just going to write a lineup to represent scalars. Well, this is the same as taking alpha out and applying T to each vector individually. Linear transformations have to obey this. But basically, that's what a linear transformation is, very briefly, very quickly. And linear transformations don't care about bases at all. They just transform vectors. But how we actually use them and apply them, well, we actually need to change a linear transformation into a matrix, and then we can apply a matrix to a vector, and then we can actually describe what a linear transformation does on that vector using that matrix. So this is just a quick intro into linear transformations. Now we have to have a quick conversation about how we actually write vectors in terms of a basis, because every vector space, V, has its own basis. And for example, here, whenever we plot things on a graph, let's just imagine we have a vector space R2, and whenever we plot a vector, on this graph, let's say, we plot this vector here, V, well, we say this vector equals 3, 2, because you go 3 times on the x-axis, then 2 times up on the y-axis. Well, what we're subtly doing here is we're saying that this vector is 3, 2 in terms of the standard basis, 3, 2, E1, E2. Whenever we plot vectors, we write them down in terms of the standard basis, because we always need to write vectors in terms of a basis. Here, we just never really notice it, because, we say E1 is the standard basis vector, where E1 just equals 1, 0, and E2 is this standard basis vector, which just goes in the y direction, so E2 equals 0, 1. And whenever we plot vectors in terms of this basis, this vector, when we actually spell it out, V actually equals 3 times E1 plus 2 times E2. But, E1, this is just the same thing as saying 3 times 1, 0 plus 2 times 0, 1. And when we actually add this together, this is 3, 0 plus 0, 2. So when we add this together, this is just 3, 2. When we, express this vector in terms of its basis, we get back the same vector. But that's why we never really notice that a vector is written in the standard basis when we plot it. But I could also choose a new basis. I could choose two basis vectors, v1 and v2 for basis here. And now, we're going to say our basis vector v1 is this, so it's 1, 1. And again, I'm writing this in terms of the standard basis. You got to be subtle. This is our vector v1. And then our vector v2 will just be 1, 0. So it's going to be over here. Our vector v2 is going to be the same as e1. Now, if I want to write the vector v, if we want to write the same purple vector or pink vector v, well, I'm going to write it as v equals 2 times v1 plus 1 times v2. This is this new vector. It's the same vector, but it's written in a different basis. So I can say that this vector v is written in the basis bv. Every vector is actually written in a basis, and then this vector v, I gotta say it's written in the basis be. It's expressed in the standard basis. This vector is expressed in a different basis. And again, if I go out and actually multiply this vector, let's say, wait, I can just delete this for now. If I want to multiply out this vector v, well, it actually equals, this is in terms of the basis v1, v2, this actually equals 2 times v1, which is 1, 1, plus, plus 1 times v2, which is just 1, 0. So this vector v will actually be equal to 2, 2 plus 1, 0, which equals 3, 2. So again, it's the same vector, and I'm expressing this now in the standard basis. The standard basis is kind of the default. We never really ask ourselves how a vector is expressed if it's expressed in the standard basis. But this shows us that, vectors depend on our choice of basis. And this will become very important for the matrix because, a matrix depends on the basis that we choose for a vector space V and for a vector space W. So if we choose different bases for these vector spaces, our matrix representing the linear transformation will be different. Okay, so now we can actually start trying to apply a linear transformation to a vector once we have chosen a basis, as we just talked about. So, T is just a linear transformation that transforms a vector from the vector space V to the vector space W, and this is basis free. This transformation doesn't care about a basis. But our matrix A, well, this will just be a tool that helps us view / understand this linear transformation once we have chosen a basis for V and W. But now let's not use this tool. Let's just try to apply the linear transformation normally. So let's imagine we have a vector from our vector space V, and this vector has coefficients b1, b2, and b3. And as we talked about, this vector is spelled out in the basis of our vector space V. And our basis, I can write it down, our basis BV has, basis vectors v1, v2, and v3. So, this is spelled out in this basis, this vector here. And now let's try to apply, I'm just going to put this on top of here. Now let's try to apply, so this is a vector from a vector space V. Let's try to apply this linear transformation to this vector. So T of, I'm just going to keep the whole notation of BV. Usually this is already implied through context. You never really write a box around V. But let's just say we apply this linear transformation to this vector. Well, this will be T of this vector B1, B2, B3. But, to kind of make it simpler, let's actually spell out this vector. What is this vector? Well, this is just this is T of B1, V1 plus B2, V2 plus B3, V3, where again, B1, these are coefficients. I'll write this, it's a conjugate sign, but just imagine this is a sign that tells you these are scalars, and these over here, these are actually vectors. So first, let's spell out the actual vector, how it looks like in the standard basis, in its raw form. And now, what we do here, because the linear transformation is linear, we can apply this linear transformation to each of the values individually. That's a property of linear transformations called the linearity, and basically we can apply and we can take the scalars out. So I'm going to do two steps at the same time. This is the same as b1 T of v1, so this equals plus b2 times T of v2 plus b3 times T of v3. This is because of linearity, we can do this. So the linear transformation doesn't act on scalars, so we can take the scalars out, it leaves them unchanged. And because it's linear, we can apply it to each vector at the same time. So this linear transformation just equals this. And this is why people say that to know what a linear transformation does to a vector, to any vector in your vector space, you just have to know what the linear transformation does to your basis vectors. If you choose a basis for a vector space and then you know where the linear transformation takes each of your basis vectors, then you can just stick on the coefficients for any vector. B1, B2, B3, these are just any scalars. So for any vector, you can just change these coefficients, and you're gonna know what the linear transformation does to your vectors. So really, we only need to know what the transformation does to our basis vectors. So let's see what, for example, just look at T of v1. What does our linear transformation do to our basis vector? Well, this has to be defined somewhere. Let's say T of v1. This will be a vector now. T takes v1 into a vector in a vector space W, because T is a transformation from vector space V to vector space in W. So this, let's just say, equals A11, A21, A31. This is a vector in W, and again, it's written in the basis of W. We can say that W has basis vectors W1, W2, W3. So again, I'm writing this linear transformation now in the basis of W, so BW. And now I just named these coefficients A11, A21, A31 because later we'll see, I can name them however I want, but these will become columns and rows of our matrix which we're going to build. So I'm just naming them in this specific way, but I can name these coefficients, A, B, C. I can name them anything. But this is a vector in W, and we wrote, this linear transformation in the basis of W, but again, we can just say, if we spell this out, what this actually is this is A11 W1 plus A21 W2 plus A31 W3. This is again written in the standard basis in its simplest, most raw form, so we can really understand it. And again, W1, W2, W3, these are just basis vectors. And this, this is the only thing we need to know. It needs to be defined somewhere how a linear transformation actually acts, on these vectors, or where it takes basis vectors. We need to have this piece of information. And once we know where the linear transformation takes these vectors, well, we can say that TV1 in the standard basis, it just equals this over here. And now we can do the same thing for TV2. We can do the same thing for TV2 and the same thing for TV3. We just need to know where it takes these basis vectors. And that now we can actually place, TV1, we can replace this over here. We can put it in here. So instead of TV1, we replace this by what we just got over here. So that our linear transformation, T of V, which we're looking at initially, which is this over here, well, this will just equal to B1 times TV1. I'm going to have this kind of bracket, but just imagine it's a normal bracket, times A11 W1 plus A21 W2 plus A33 W3. This is this factor over here, and then plus B2 times TV2. Well, where does T take our basis vector V2? Again, it just takes it to another vector in W, and we can just name it. We can name it A12, A22, A32. We can name it like this. And again, this is written in the basis W1, W2, W3. I'm just naming the coefficients in a very specific way so that when I line them up in the matrix, it's gonna make sense because we'll later build our matrix with this. But again, so this will be B2. A12 W1 plus A22 W2 plus A32 W3. And now again, as you're already guessing, then we do plus B3 of this TV3. Well, TV3, let's just say it takes our matrix, it takes our vector into the vector 1 A13 W1. I'm writing it out in the standard basis. A23 W2 plus A33 W3. This is our vector. We had a vector from our vector space V, and our linear transformation took this vector into a vector in W. And again, I wrote this vector in our basis BV, and this vector here, well, this vector here right now is expressed in the standard basis because it's expressed in the standard basis, so we really spelled everything out. But now we're basically done. We have made the transformation. Now we can actually go and start building a matrix because, we usually don't have the information of what it does to our standard. We don't usually have the information of what our linear transformation does to our chosen standard basis vectors. Again, we could have chosen a different basis, and then all this would have been different. Usually we're just given a matrix that represents linear transformation, and now we can start building up this matrix and see that it'll actually be way simpler that way. So again, now to start building our matrix, first of all, let's factor out our basis W. We want to write this again into W. We want to write this vector in our basis of W because our vector space W has a basis that we have chosen for it, and that basis is W. So we can factor out all the W, so we can say that this equals B1 A11 plus B2 A12 plus B3 A13 W1. So we're just factoring out the W's plus B1 A21 plus B2 A22 plus B3 A23 W2. Again, this is kind of tedious. We're just trying to factor it out now because we'll see why it's going to come in very handy. B1 A31 plus B2 A32 plus B3 A33 W3. So we factored out our basis vectors, and now what we can do is we can try to line up our now let's start doing some interesting things. So first of all, let's try to line up this into columns because we're going to see a nice matrix is just going to pop out of this. So let's imagine we line it up like this, and now what we see is that this is our vector. We have here B1 b2, b3, and again b1, b2, b3, b1, b2, b3. This is this vector. Our vector v that we have chosen is b1, b2, b3 in our basis bv, and this vector is from v. And this vector can depend, we can choose a different vector, and then we'll have different coefficients, b1, b2, b3. So now we're saying we're going to take all these coefficients out. We'll put them out, b1, b2, b3, into a vector. So we're taking these coefficients out into a vector. We're removing all of them. And then you can kind of see why we're already defining matrix multiplication how we are. Why we're defining matrix vector multiplication how we are. To actually, calculate this, once we'll turn this into a matrix, we'll just, calculate this vector. We'll have this vector over here, and then, we just rotate it each time, multiply it by this side, then you go down, multiply by this, multiply by this. So this is kind of, we're seeing where this actually idea of vector matrix multiplication comes from and why we're actually doing it. So we're taking this out, and then what we're left with, once you remove all these values, we're just left with a11, a12, a13, w1, plus all this, and this is all written in the basis w1, w2, w3. Now we can just say we create a matrix out of these values. We say a11, a12, a13, and we don't write w1 here, but we just assume that these coefficients come from the basis of w1. This is why when people write a matrix, we're silently assuming this is all expressed in the w1 basis. And then again, we have a21, a22, a23, and a31, a32, a33, and again, these are written in the basis of w2, these are written in the basis of w3. And now we can actually see, well, what is a11, a21, a31? Well, this, if we just scroll back up, this is exactly the coefficients of where our matrix takes our initial vector v1. Our transformation took our vector v1 to the coefficients a11, a21, a31 in our basis of w. So this column over here, well, that's just tv1 written in the basis of bw. This is just a vector. This is kind of so clean, and this is where we just constructed a matrix, and we can see that these columns are just where our matrix takes our basis vectors in our basis of our new vector space. And again, this is tv3 in bw, and this is why we can see that a matrix actually depends on your chosen on the chosen basis, because if we chose different vectors v1, v2, v3 for a basis of v, then these coefficients would be different. And also if you chose a different basis, then these coefficients would also be different. So all these coefficients here, these coefficients depend on the basis that we choose for v, because these vectors would be different, and they depend on the basis of w, because then again we could express these completely differently in a different basis. And so we have this special box we just made here, and then we have our vector which we took out, b2, b1, b2, b3, and this is just our vector from our vector space v. And now to apply a linear transformation, we just created this matrix. This is a matrix A that represents our linear transformation, in the specified bases of v and w. And now to just apply linear transformation, we can just change this vector. We can say this vector is any vector. And if we want to see what a linear transformation does to that vector, we just multiply this vector out with this matrix, and we multiply this by this to get the first coefficient. So this will be, b1 a11 plus b2 a12 plus b3 a13. This will be the first value. Then our second value will be this multiplied by this, and then this multiplied by this. And again, this will be a vector expressed in the basis w1, w2, w3. And this is exactly what we got by ourselves over here. Once we this is the answer we got, and then once we factor out w, we got this exact same vector. This vector over here is just this vector over here. Once we factor out the w, we didn't need a matrix at all. But here we can see why matrices become so useful. Once we define a basis for v and w, we can create a matrix, and then we can just multiply any vector by that matrix, and it outputs a vector which outputs a vector which is already expressed in our basis of w, and it makes using linear transformations so much more practical. In conclusion, we show that matrices aren't necessary to define a linear map, a linear transformation, but they are very useful. They make computation much faster, especially on a large scale and for computers to use. And also, the vector matrix multiplication, I said it's defined this way because of how we calculated it. But there's also different reasons of why it's defined this way also for compositions of matrices. So it's a little bit more complicated, but we basically saw that matrices technically in this sense aren't actually necessary to understand what a linear transformation does. They're just tools, and also now we can see why someone can say that a matrix of A can technically be a function of three variables. It's a function of our linear transformation T, and of our basis V, and of our basis W, if we assume that T is a linear transformation from V to W. Because if this basis changes, or this basis changes, then the matrix can still represent the same linear transformation, but it will look different. It will have different coefficients, A11, A12, A13. And also, of course, if the linear transformation changes, then also our matrix will look completely different. So technically, matrix is a function with three variables. It depends on all these three things. And yeah, so I hope you enjoyed this video. I hope it kind of gave you a deeper intuition of what matrices actually are and how we technically don't really need them, and also vector matrix multiplication. It's not super necessary in this case to see what a linear transformation does to our basis vectors, but we do of course actually need to know what our linear transformation, this has to be given somewhere. We need to know what a linear transformation will do to our vectors, either in the standard basis or in already a previously given basis. Alright, one last thing, just a quick example. This video is going to be way too long, but let's imagine we have a linear transformation, from f2 to f3. This is just a field, and let's say the linear transformation is defined this way, so it takes a vector xy, a 2D vector, and it outputs a 3D vector. So we can imagine, this is a linear transformation from a 2D space to a 3D space, and this is how it's defined, but again, now we can see, first of all, what we can build a matrix for this linear transformation. Let's say in the standard basis. So what does our matrix do to the standard basis, to the standard vector e1 and to the standard basis vector e2? Well, it takes it into 1, 2, 7, and it takes our basis vector e2 into 3, 5, 9. And again, this I'm expressing in the standard basis of our F3 field, or of our three-dimensional space. Again, E1, E2, E3, and in this case, our standard basis vector E1 just equals 1, 0, 0. When we go to a 3D space. So this is where a matrix takes our basis vectors. So now, if we make a matrix A, in the standard basis of our space, of our initial space, and also the standard basis of our other space, usually epsilon's in order for the standard basis. Well, this matrix will just be 1, 2, 7, 3, 5, 9, because again, this is where our matrix takes our standard vector e1 written in the standard basis of our vector space, of our F3 vector space, and again, this is where a matrix takes our vector space E3 written in this vector space. And these vectors are all written E1, E2, E3 in the standard basis of this vector space. And this will be a matrix. So now we can multiply any vector by this matrix, so we can multiply any vector, for example, like xy by this, and we will get outputted a vector which will be in this field over here. And again, this matrix just represents this linear transformation over here in the standard basis. We could have also chosen a different basis. This is the example. Thank you for watching, and goodbye.